All right. How do inverse trig functions look? Well, okay, first off, how do we define inverse functions? What are inverse functions? Yes, that's exactly what it is. So if we had y is equal to 2x plus 3, to find the inverse, switch x and y, and then solve for y. So here's our original function. To find the inverse, switch x and y, and solve for y. So we subtract 3 from both sides first. And then divide by 2. How do we differentiate? How do we distinguish this being inverse as opposed to this being the original function? What tells it apart? That -1 exponent means that it's the inverse. The inverse function. That -1. Not a negative, because if you just put a negative up there, then it's a reciprocal. If you put a 1 up there, it could be a derivative, f prime. So I put f -1. How, okay, now, because the first step was we switch x and y, the domains and ranges are switched. So the domain of your original function is now the range of your inverse. The range of your original function is now the domain of your inverse. Because you switch x and y. In other words, if our solutions were 1, 2, 5, 7, 6, -3, let's say those are our points for our regular function, then the points of our inverse function would be switched. You just switch x and y. That's important because it becomes, for algebraic equations, it's not a problem. But when we go to trigonometric functions, it now becomes a problem. For example, sine x. The graph of sine x The sine function is bounded by 1 and -1. So at 0, what is sine? Think of the unit circle. At 0, remember the sine deals with the y-axis, the y values. This is 1, 0. So at 0, sine is 0. At pi over 2, it's 1. At pi, it's 0. At 3 pi over 2, it's -1, and it continues in this cyclical manner. So that's y is equal to sine x. When we talk about the inverse of trig functions, we can also call them arcs. So sometimes you'll see it as an arc sign, as sometimes you'll see it with a -1 exponent. Now, when we're dealing with the inverse functions, the arc trig functions, the inverse trig functions, up here we put the angle pi over 2. If I put pi over 2 in there, what do I get? 1. Here I have to work backwards. I put the radian measures. If I put 1 inside here, what is the inverse of sine at 1 is equal to pi over 2. So here I put the answer, and here I get the angle. You have to think of backwards, of doing things backwards when we deal with inverse functions. So what's the graph going to look like for the inverse sine? You know, it's hard when you first think about it. It's hard to picture it. Basically, remember I said we switch x and y. So the y values, the domain is what? First off, the domain of sine is what? Domain of sine is all real numbers, -infinity, +infinity. What's the range of sine? Yeah, -1 to 1. So here for the inverse, we got to switch. So the graph of the inverse of sine on the x-axis goes from -1 to 1, and it goes up and down. That's what the hyperbolic or the inverse, the arc sine is going to look like. And the inverse cosine is going to be similar. It's just shifted 90 degrees. Remember what the tangent looks like? What is tangent? What is it made up of? Sine over cosine. Because it's a rational expression, what can you not have on the bottom? Zeros. So if you think about it, what values of cosine gives me 0? Pi over 2. Pi over 2 and negative pi over 2. It's got a period of 1 pi units wide, from negative pi over 2, pi over 2. At 0, so these are my vertical asymptotes. The graph cannot cross these vertical asymptotes. At 0, what is my function? Sine of 0 is 0. Cosine of 0 is 1, so it's 0. How about pi over 4? Sine pi over 4 over cosine pi over 4 is what? 1. At negative pi over 4, it's going to be negative 1. So the tangent function is an increasing function. Kind of looks like the cubic function. It looks like this, and it keeps on going forever and ever. It looks like that forever. So the inverse tangent function, remember, we switch x and y, switch the domains and ranges. Which means since my period here was negative pi over 2, pi over 2, I do the same thing here. So now these are my horizontal asymptotes. At 0, it's 0. So there's the graph of the arc tangent. What about cotangent? What's cotangent made up of? Cosine over sine. So where is sine equal to 0? At 0, and where else? At pi, negative pi. So these are my vertical asymptotes. Now, same as the way sine and cosine are shifted 90 degrees, so are tangent and cotangent. They're shifted 90 degrees. So the inverse of cotangent it goes from 0 to pi. So those are my bounds, and it's pi over 2 is 0. Pi over 4. Oop, hold, time out, time out, time out. At pi over 4, it should be 1. So I'm sorry, this is a decreasing function. It's a decreasing function. Because at 0, it's undefined. At pi over 4, it's 1. At pi over 2, it's 0. At 3 pi over 4, it's -1. So it's a decreasing function, which is why it's flipped. It's a decrease. The tangent's increasing, cotangent's decreasing. Again, same thing. The domain of the cotangent function is from 0 to pi, positive, negative infinity. So that means it's positive, negative infinity on the domain and 0 to pi on the range. How about let's do secant. What does a secant function look like? What's the formula for secant? That sounded pretty confident. Well, yeah, the rule I think about is they cannot have the same first letters. It can't be 1 over sine because sine and secant have the same first letters. So it's got to be cosine. It's a fraction, so it has asymptotes. Where is cosine equal to 0? Pi over 2, negative pi over 2. Those are my vertical asymptotes. The easiest way to graph a secant function is first start off by graphing the sine cosine function. Anywhere it crosses the x-axis is your asymptote. So that's the cosine function. What is you secant is the reciprocal of it. So they share the same vertex, but now I go up. Now here I go down. Here I go down. That's the easiest way of graphing the secant and cosecant functions. Because you have your asymptotes, they share something, and it has to approach infinity or negative infinity. There are no x-intercepts in a secant function. Notice now the graph, because it shifted up relatively pi over 2 units. This is one negative one, and it's a domain of there. Make that pi over 2, make it bigger. Because at pi over 2, negative pi over 2, we have asymptotes. We can't cross that. So what happens on this side from here? We have negative pi, and here we have pi. So what happens to our graph? This is at -1. This is at +1. Because that's where our function starts. So what happens in our graph here? From pi, we have from here, and from here at pi here, we go up. We don't have anything within the negative pi over 2, pi over 2, within that first part. Within here and here, we have nothing inside here. So between there is nothing. So that, like that. Similar in the cosecant, which is 1 over sine. The inverse is cosecant inverse. Again, first draw the sine function. Since these are my asymptotes. My vertical asymptotes of my secant function are where sine is equal to 0. So those are the graphs. Now these go on the inside. So those are the graphs. That's what they represent. And how do we find them? It's again, it's you switch x and y. In the arc functions, the inverse functions, I give you the answer. You have to give me the angle that makes that the answer. For example, if I give you that, what would be the answer? Yeah. So it's asking for what angle gives the sine function an answer of 1, a value of 1, pi over 2. Or again, it's pi over 2 plus 2 pi. Or n pi. All right, let's look at the definition here of the inverse functions. And then y equals the inverse of tangent. No, that's not a tangent. We're doing with sine. The inverse tangent or the arc tangent is a number in the domain of negative pi over 2 pi over 2 for which the tangent of y equals x. Remember, now we're talking about the radians gives you an angle. The inverse cotangent function. A number in the domain 0 to pi, but just shifted pi over 2. The cotangent of y is equal to x. The inverse secant function, a number in the domain 0 pi over 2 union pi over 2 to pi, for which secant y equals x. Lastly, y equals the inverse of cosecant is a number in negative pi over 2 to 0 unioned with 0 pi over 2, for which the cosecant of y is equal to x. Let's look at examples here. The beautiful thing about this is to find the derivatives of these is formula based. So here's example 1. The inverse tangent of 1 radical 3 is equal to what? And B, the inverse tangent of negative radical 3 is equal to what? Graphically. Remember, tangent is sine over cosine, right? So the sine function is on top. That deals with which? The x or the y axis? That which one? Y axis. The cosine deals with the x axis, the sines deal with the y axis. So the sine value is 1. Let's say that's 1. And the cosine value is pi over 3, or square root of 3, I mean. Where these 2 points intersect, what angle does that satisfy? The cheat sheets I gave y'all are sent to y'all. It has all that stuff in there. It just breaks it down. So which at pi over 6, what is the value of the tangent? What is the sine of cosine? It's 1 over radical 3. In this one, same thing here. Now we're doing a negative angle. This is over 1. So sine over cosine, sine is the y value. And so that one is going to go to its negative angle, pi over 3, since it's in the 4th quadrant. Where is tangent negative? At which with quadrants? No, because remember, in the 3rd quadrant, the sine and cosine are both negative, so tangent's positive. In the 1st quadrant, they're both positive, so tangent's positive. In the 2nd and 4th quadrants, tangent's negative in the 2nd and 4th quadrants. Because one of the values has to be positive, one of them has to be negative in those quadrants. The derivative of the inverse function of sine. So to begin with, we have to define things. We have to define our function as sine x and the inverse function as that. Why is that important? Did we learn a formula to learn the derivatives of functions like this? Yes, in 2 sections ago. We had this formula. So the derivative of the inverse is equal to 1 over the derivative times composite of the inverse function. Remember that formula? We did it, I think, 3 sections ago. To find the derivative of the inverse function, you have to have the derivative of the function first and the inverse function itself. It's a composite function there. So what do we do first? Find the derivative of my inverse function. I'll write down this. So start plugging things in there. What is my derivative of f? F of x is sine. What is the inverse, or what is the derivative of f? If f of x is sine x, the derivative is cosine x. So that's this outer function. And what goes inside there? The inverse function, which is the sine inverse of x. Identity function. What is the cosine? So let's isolate this for cosine. 1 minus sine squared u, square root both sides. So cosine u is equal to square root of 1 minus sine squared u. Why is that important? Because now instead of cosine, I could use this function. One minus sine squared u is what's inside there, the inverse function of x. So far, so good. Now, sine squared times inverse sine. Equals sine inverse squared. So these cancel, so it's x squared. So this becomes x squared. Because sine squared so there's my derivative of if I have the inverse of some composite function, then it becomes 1 over square root of 1 minus u squared times du dx. This is just with x, but if this was an equation x, like inverse sine of x squared plus 1, we have to use this. So these are two formulas we'll use. Example. Find the derivative of the inverse of x squared. So in here, My u is what? Is x squared. So I can just use this formula now. Because once this x changes to anything else in the equation, I cannot use this function. I got to use this one, the sine u. So this is my u right here. So I have 1 over square root of 1 minus x squared squared times the derivative of u. The derivative of u is 2x. So it's 2x over square root of 1 minus x to the fourth. That's my answer. And it's similar to finding out the derivatives of all the other functions using the same logic we just did there. Derivative of y equals the inverse of tangent u. So to find, if this is my function, to find the derivative, we have to first define our function tangent x. We have to find the first or the inverse of it, which is tangent of inverse of x. We have to find the derivative of f, which is what? What's the derivative of tangent? Anybody remember? If you don't remember, we can always figure it out. Tangent is sine over cosine. And from there, we could do the quotient rule. So we have sine over cosine. Derivative of sine is cosine. Derivative of cosine is negative sine. If cosine, cosine says cosine squared x minus negative sine squared x, which makes it a positive sine squared x, all over the denominator cosine squared. So we have identity cosine squared plus sine squared is 1. So it makes it into secant squared x. Again, you don't have to memorize these things. You can always figure it out yourself. So the derivative of the inverse tangent of u using our formula that we had earlier, remember, the inverse function derivative is equal to 1 over the derivative times the inverse. That's the formula we'll be using. So we have 1 f prime f inverse of x, which makes it the derivative is secant squared of tangent inverse Now, trig identity. Remember, it's cosine squared plus sine squared equals 1. If I divide everybody by cosine, the secant is 1 over cosine. So if I divide everybody by cosine squared, I get 1 plus tangent squared equals secant squared. So this secant squared is the same thing as 1 plus tangent. 1 plus tangent squared times inverse tangent of x. One plus tangent times tangent inverse is t, so it's squared, so it's x squared. So there's my formula for the derivative of tangent. And here's the general formula. Example. It is the same process as because our inverse was tangent, we had to make the outside function tangent. Because the tangent, remember this property, that the secant of a inverse secant of x is equal to x. The function and its inverse cancel each other out, so you just have to put the operation. And that's why we needed tangent out here, because we had inverse tangent here. Let me see. We had a derivative of x of secant. Remember, the secant and cosecant, they were shifted off the x-axis by pi over 2 to pi. So if x is greater than 1, we have this formula. If x is less than 1, or negative 1. Remember, between -1 and 1, the secant and cosecant don't exist. They're shifted off pi over 2 units off. And the formula for secant is equal to 1 over absolute value of u, square root of u squared minus 1, du dx. Really quick, let me show you this. Find the derivative of this one. So find d dx of inverse of secant of 5x to the fourth. So using our equation here, we have 1. This is our value of u. That's u. So we have the absolute value of 5x to the fourth square root 5x to the fourth squared minus 1 times the derivative of u, which is 20x to the third. Since 5 is positive and x to the fourth can never be negative, we don't need the absolute values. 5 goes into 24 times. X cubed and x fourth cancel, leaving you with just x on the bottom. 25 squared, 25 x to the eighth minus 1. And there's your derivative. Really quick, take a picture of these. These are all of the formulas form.
How do we know to put the absolute value in?
What's that?
How do we know to put the absolute value?
You put the absolute value in there because that's part of the formula. But since our value is 5x to the fourth, it can never be negative.
Oh.
Yeah, see, it's part of our formula right here. See, absolute value of x, u. And only reason we have to keep it there is if our exponent is odd, which means the answer can be positive or negative. All right. That's the end of section, end of chapter. The reason I'm saying yay is because now we're going to start into chapter 4. And we're going to start looking at graphs and compositions of graphs. And then we can move into the last chapter, which is integrals.